Hi. So what we are basically trying to do right here is to verify that the second partial derivative with respect to x plus the second partial derivative with respect to y is equals to 0 for the function f of xy that is given as a tan inverse of y over x. Okay. So one of the key things to solving this question is being able to find the derivative of tan inverse of y over x. Here's how we do it. So what I'd want to do is instead of me using f of xy, let me present this as z equals to uh, tan inverse of y over x there. So what I would do here is that instead of writing it as an inverse, I can write to say y over x is equals to what? Is equals to tan z like that. So I can use a right angle triangle for this. Okay, I'm just looking for the derivative of that. Okay, so instead of looking for the derivative of the inverse just the way it is, I'll just try to manipulate it so that I get what I need. So right here you observe to say if this angle here is z, remember according to SOHCAHTOA, tan theta, or in this case tan z, is equals to opposite over adjacent, and in this case our opposite is y and our adjacent is x. So you observe to say your hypotenuse, if you use Pythagoras theorem, it's just going to be the square root of x squared plus y squared like that. Let's go ahead and find the derivative now. So you observe to say you have y over x is equals to tan z. So if I differentiate, but how am I really differentiating here? So this is how this is going to be. It's going to be more like dy x dz. um, dz here is just going to be equals to, like, the derivative of tan z is nothing but what? Sec squared z like that. Okay, so remember to say this can also be written as 1 over cos squared z, and it's much convenient to use cos because like this triangle can give us identities such as cos, sine, as well as tan. So I would not want to use sec squared because I don't really know what sec is in terms of this triangle here. So remember, we are looking for the derivative with respect to, the derivative. It's more like you're looking for dz uh, dyx. So it's like you are differentiating with respect to y over x. So remember here you have dy over x dz. You are given as that, or that's what we get. But if we flip it, like more like the reciprocal, it's just going to be cos squared z like that. Okay, and you observe to say this is just going to be, I'll say open bracket. So cos z, like cos z on the triangle here, right angle triangle, is going to be the adjacent divided by the hypotenuse, which is x divided by the hypotenuse, which is the square root of x squared plus y squared like that. Then we say squared. So you observe to say the derivative of this, the derivative of that will be nothing but um, what we have here, of which if we write as dz dy, then we have x there is just equals to what? X squared divided by x squared plus y squared. We cancel out the square root plus with that square that we have there. So that's the derivative of tan inverse of y over x. That's how we find it, and that's very important there. Okay, so now what is remaining is now for us now to be finding the derivatives both with respect to y and with respect to x. So how is this is going to be is that if I say f of x like this, like the partial derivative here with respect to x, this is just going to be equals to the derivative of tan inverse, which we have found as x squared divided by x squared plus y squared. You're going to multiply this by the derivative of the angle, which is y over x with respect to x. That's just going to be minus y over x squared. So if you differentiate this angle with respect to x, that's what you're going to get there. You're going to get minus y over x squared. In case you're confused of how this is coming about, instead of writing y over x, I can say it's y then x to the negative 1, of which if the negative drops, you're going to have minus y here. And that's going to be x minus 2, of which this is just minus y over x squared. That's where that is coming from. Okay, so now this you observe to say that and that can go. So what we remain with is just minus y over x squared plus what? Plus y squared. That's the first derivative. So now to find the second derivative, remember we're looking for the second partial derivative. We can use the quotient rule here. My u is my numerator, which is minus y. Then my du, or my u prime will be equals to what? Will be equals to 0. Why is it 0? It's because I'm differentiating with respect to x, not with respect to y. So I'm treating y as a constant. So if you say v, which is your denominator, which is x squared plus y squared, if you differentiate that with respect to x, you're going to get 2x. So you observe to say your f of x like that is just going to be um, your u prime by v, of which this is 0 multiplied by this one here, just going to be 0. That would be minus, okay, minus u. Okay, what is our u here? Our u is minus y. Okay, our u is just negative y there. Okay, so you can say minus y like that. Then what is our v prime? Our v prime is positive 2x. That's just divide by v squared. That's going to be x squared plus y squared. We put them in brackets, squared like that. This is just going to be positive 2xy divide by x squared plus y squared. Then that's going to be squared like that. So this is the second partial derivative of that function that we have with respect to x. Okay, so we can place it up here. So our second partial with respect to x, we have found that is equals to 2xy divided by x squared plus y squared squared like that. Okay, now let's go ahead and find the second partial derivative with respect to y. So if we say fy is equals to, we are still going to say the derivative of the function itself, which is tan inverse, which is still x squared divided by x squared plus y squared. You're going to multiply this by the derivative of the angle with respect to y, which is just going to be 1 over x. If you differentiate the angle here with respect to y, you're going to get 1 over x, of which you observe that this one goes and that one goes there, and you just end up with what? Just end up with x over x squared plus y squared. So now, all the same, you can still use the quotient rule here, because that's the first derivative, the first partial derivative. So you can now come up with your second partial derivative. So you can say what u, which is our numerator, is equals to x, meaning our u prime is going to be 0. Why is it 0? Because I'm differentiating with respect to y, so I'm treating x as a constant. So our v is still the denominator, which is x squared plus y squared, meaning our v prime is going to be 2y. So you observe to say you're going to have a second partial with respect to y being equals to your u prime, which is 0 multiplied by v. This one and that one will give you 0. Then you're going to say minus your u, which is your x, okay, multiplied by your v prime, which is 2y, like that. Then that will be divided by your v squared, which is going to be x squared plus y squared squared, like that. This is just going to be equals to minus 2xy divided by x squared plus y squared squared, like that. And there we have it. So we have obtained to say our second partial with respect to y is equals to minus 2xy divided by x squared plus y squared squared, like that. Okay, so now remember, what we are trying to verify is the fact that our f of x, our second partial with respect to x plus second partial with respect to y is equals to 0. So if you bring in your this part here, the second partial with respect to x, which is your 2xy divided by your x squared plus your y squared squared, like that, then you're going to put this one, which is the second partial with respect to y, which is minus 2xy divided by x squared plus y squared squared and you observe that this is going to be 0, hence we have what? You have verified. And that's all that we're required to do. So it's just a matter of knowing how to treat partial derivatives. If you are differentiating with respect to x, treat everything else but x as a constant. If you are differentiating with respect to y, treat everything but y as a constant. Okay, so and again, I believe the most important part of this question was to knowing how to differentiate an inverse trig function, and you can use this trick when it comes to any other trig function that you can be given, either it's cos, sine, sec, cotangent, secant, so on and so forth. They are still going It's still going to work as well, provided it's an inverse. You just swap it. It's more like if you're given y to be equals to let's say sec inverse of x, you can still write this as x is equals to what? X is equals to sec y, and then just manipulate this, and it gives you exactly what you are looking for. So that's so in this video. Thank you very much for watching.